Now, I mentioned this as we were going through the header types for TCP, the idea of window sizing. Now, window sizing of 1, which is actually used by some protocols. It's not used necessarily by TCP, but some protocols, say our routing protocols like EIGRP, which is Enhanced Interior Gateway Routing Protocol, does use a window size of 1. But in the case of TCP, TCP actually doesn't do this. I'm just using this as an example here. And this example is specifically to show how the forward acknowledgement process works. So when we're sending messages from A over to B, we send sequence number 1. When the receiver gets it, we send an acknowledgement back saying that we got it. But notice how we're acknowledging it. We're acknowledging that the next thing we're expecting is sequence 2. Then we send sequence 2, and we acknowledge that the next thing we're expecting is sequence 3, and so on and so forth. Again, this example would be a window size of 1, which isn't something we'd necessarily do. What would be more likely is something like this. Having a fixed window size, in this case a window size of 3, the sender sends segment 1, 2, and 3. We then acknowledge that 4 is the next thing we're expecting. We send 4, 5, and 6, and then we acknowledge 7, and so on. This also isn't how TCP works. TCP doesn't have a fixed window size. It actually has what's called a sliding window. We start with a low number and then gradually increase that number as we continue sending segments back and forth between the devices. So to show a sliding window, well, actually we're going to show a sliding window actually going the other direction here with this example. We're going to start with a window size of 3. So we send segment 1, 2, and 3, but segment 3 gets lost in transmission. So segment 3 is lost. The receiver, after waiting a while for 3 to show up, then sends an acknowledgement back saying we're acknowledging that 3 is the next thing we're expecting. And we're dropping our window size down to 2 because, well, we didn't get the data we were expecting. So we send the message back. The sender, realizing that the window size is now decreased from 3 to 2, seeing the other size is slower. We can only go as fast as the slowest window size agreed upon between the two sides here. So if the receiver says the window size is 2, we have to send with a window of 2. So what we do here is we resend 3 and then send 4, which would be the next thing here for a window size of 2. The receiver then acknowledges 5 as the next thing. Now, if the receiver, took care of some other connections or sped up its bandwidth, it might come back and say the window size is now 10. At which case we're going to send not 10 but 3 because the sender now has the smaller window size of 3. If we increase that to say 6, now we'll be sending 6 segments back and forth. Again, agree upon whoever has the smallest window size is the window we're going to use. Now, what really truly happens here with TCP is because of the TCP slow start mechanism, we start off with a relatively small window size and then ramp up until we end up filling up the buffers or filling up the bandwidth between the two. We slide back down, ramp back up, and go through this roller coaster process during a TCP session of increasing and decreasing the window size throughout the entire TCP conversation. But we actually use quite a bit larger numbers here in the case of TCP than even 3, 2, and 10, the examples I've given here in this particular slide. All right, so let's put this all together with port numbers. In this case, I've got a host, host A talking to host B again. We've got a random source port of 1028, and we're talking to port 23, which just so happens to be Telnet port. All right, so we're sending that. We've got a sequence number that we've picked out as 50, and we're acknowledging that the other side we're expecting 1. So we send that over. We sent 50 bytes. Now, the return responds back and says, again, notice the source destination ports have flipped. The sequence number is being sent as 1, and the acknowledgement number is 51. There's a slide note here. We have to change the acknowledgement number in this slide. So the acknowledgement number being sent back is 51. We respond back and then set our source port to 1028, destination 1023, so we switch those back, and then sets the sequence number. Notice the sequence number is 400. We don't actually go in sequential sequence numbers. Going in sequential sequence numbers for TCP is paramount to a attack waiting to happen. There's something called a TCP hijack mechanism that allows us to hijack existing TCP sessions So in this particular case, we picked the next random sequence number in the set. We then send things in order during the window size, but then we increase to another random TCP number as we go through here. So we're using sequence number 400 for the next set of data. We send that. We got 350 bytes sent. We're expecting, we're doing forward acknowledgement for 2. That sends back the other direction. The receiver flipping the source and destination port has, responded back with sequence number 2, and the acknowledgement number here is forward acknowledgement for, packet number 401. So that seems to work well. Everything is being sent back and forth between these two devices.